questions. We'll have two teams. Each will have about 20 minutes to speak and 10 minutes of Q&A afterwards. Please, if you're on Zoom, make sure you're muted. We can hear some noises from over here. And if you do want to jump in at the end, we'll have a little bit of a Q&A panel session. So feel free to raise your questions in the chat so that we can address those afterwards. Without further ado, because we have very little time, we've got a strict time schedule today, I'll introduce our first team, the CHAR satellite imagery team.
Hi everyone, thank you for joining us today. Today we're presenting our project on machine learning augmented prediction for waiver exploitation detection. This is the result of our 8-week work in the Stanford Data Science for Social Good program, organized by Stanford Data Science in collaboration with the Stanford Human Trafficking Data Lab. Here's a quick overview of our team. 3 of us are all DSSG fellows. My name is Enkhjin, and I'm a senior at Stanford University studying data science, and I'll let my teammates introduce themselves.
Hi, I'm Leon. I'm a rising sophomore. I'm likely a math major.
Hi, I'm Kyler. I'm a rising sophomore. I'm likely a data science.
And we've been fortunate to work with a great group of mentors, Dr. Benjamin Seiler, Dr. Kim Babiards, our technical mentors, Dr. Mike Bayoki, our faculty mentor, and Jonas Jr., who also provided additional technical support. So for background, modern slavery is a global crisis affecting an estimated 50 million people annually, many in forced labor situations. For victims, escape is extremely difficult. They often face situations like physical isolation in remote work areas, confiscation of identification documents, constant surveillance by exploiters, threats of violence against themselves or their families, and language barriers and unfamiliarity with the local laws and resources. And the lack of reliable data on these hidden populations makes it challenging to implement effective policies for prevention and rescue. So the Human Trafficking Data Lab aims to use data-driven approaches to detect and combat forced labor. For the past 4 years, the lab has strategically focused its effort in Brazil, and this is due to several factors. First, potential for impact. Over 1 million people are trapped in modern slavery conditions in Brazil. Second, the country's strong administrative record-keeping environment makes it provides a wealth of data, and the well-established transparency laws make this data accessible, creating an ideal environment for the lab's work in detecting and analyzing trafficking patterns. And lastly, the lab has established a strong collaboration with Brazil's Federal Labor Prosecution Office, which is a key actor in the country's anti-trafficking response and policy agenda. And due to these reasons, Brazil serves as the lab's initial country study with the potential to expand its approach to other regions in the future. Within Brazil, the lab chose to focus on the charcoal industry due to its labor-intensive production process and high risk of exploitation. Charcoal production involves cutting down trees, often in remote forest areas. Workers must stack wood in large brick kilns and monitor the slow burning process, which can take days. The work is physically demanding, involving heavy lifting and exposure to extreme heat and smoke. The remote locations and demanding nature of the work make it easier for exploiters to control workers. Workers are often living in on-site in poor conditions, isolated from outside contact. And the industry frequently targets vulnerable populations like immigrants or those in extreme poverty. Charcoal production is also a significant driver of deforestation, often carried out illegally. And the industry is key to Brazil's steel production, creating economic pressure to maintain operations. And traditional monitoring methods are limited due to remote and transient nature of sites. And most importantly, satellite tracking offers a promising method for tracking these hidden production sites. So our project builds upon an existing process for detecting charcoal sites. And this process starts with gathering satellite imagery and using a remote detection model called CHAR and developed by the lab, and employing human post-processing to filter the model's findings to select sites for task force inspection. So let's talk more about the CHAR model. These are satellite images of charcoal production sites. And these are what the CHAR model aims to flag. In each image, we can see rows of rectangular structures. These are the charcoal kilns. The kilns appear as distinct repetitive patterns against the surrounding landscape. They're often arranged in parallel lines, which is a key visual signature for the detection model. And notice how the sites are situated in cleared areas, often near forested regions, indicating recent deforestation. And the surrounding areas show signs of human activity like cleared paths, vehicle tracks, and sometimes small structures nearby. While the previous slide showed clear and high resolution images, the reality of our detection process is that the CHAR model relies on high frequency and low resolution images. So as you can see on the right image, the level of detail is significantly reduced compared to what we just saw. And this lower resolution creates challenges for accurate detection, like, for example, structures with parallel or straight lines can be mistaken for a row of charcoal kilns. These can be like roads or like small rivers, and these can trigger false positives. And what this means is that the model sometimes flags sites that aren't actually charcoal sites, and which is why currently human post-processing is necessary to filter out the false positives. And our project aims to improve this process by creating another machine learning model that incorporates geospatial covariates to distinguish true charcoal sites from similar looking structures, even in low resolution images. And Leon will talk more about these geospatial covariates. This addition aims to both improve the accuracy of the detection and reduce the workload in the human post-processing stage. So for the past 8 weeks, our goal was to elevate the human post-processing by developing ML models, exploring geospatial data, analyzing feature importance, and lastly, expanding the training data.
Cool. So I'm going to chat to you now about feature engineering. That is, how did we construct the relevant geospatial covariates into our model? So in particular, we constructed 2 metrics, density metrics and distance metrics. So I'll talk a little bit more about what those actually mean. So first, I'm going to give you an overview of the data that we're working with. There are 2 salient features to point out here. The first is that there are in total 5,278 sites that are flagged by the model. All of these sites are in the state of Marignao, and they have a threshold value of 0.9. So all this means is that the model predicts with greater than 90% probability that it thinks it's a true charcoal site. The second salient feature is that we have 478 true sites, which were manually labeled and then confirmed as charcoal sites. So this represents about 9% of our data set as true positives. What else do we have? We also have the model score, as I flagged. We also have the month. So we have multiple images taken over time since July of last year up to March of this year. We have the geometry. So that is the precise location of the flag site on the planet. So you can think of this as like latitude and longitude. And then we have tiling. So the satellite image is like grouped into many, many different small tiles of the entire state, or the whole world actually. And they have a unique tile ID. So this is important because it allows us to group the images over time so that we're not repeating the same image into the model which Kyler will talk a little bit more about that. So what does all this actually look like? So here's a map of the state of Maranhão, Brazil. And here's all of the different sites and the false positives in blue and the true positives in red. I think at first blush, like there is nothing obvious here to suggest that there's an easy recognizable pattern to say, oh, well, we think charcoal sites tend to be in this part of the country near this feature. I might point out that the middle of the country and the northwest of the country looks suspiciously empty, but beyond that, there's nothing really here that we can infer directly. So why is this important? This is important because it affects how we're going to think about our model, and it affects what data we want to put into our model. So our initial model intuition comes in 4 key respects. First was roads. So charcoal needs to be transported to steel mills, which is why the industry exists in the first place. So we would expect that the charcoal production sites are somewhat close to the roads in the first instance. Second is deforestation. Somewhat unsurprisingly, charcoal is made from cutting down trees. So we would expect the charcoal production sites to be close to where deforestation has occurred recently, or where we can see deforestation sites. Third is villages. This might go in both directions. So charcoal sites, on one hand, might want to be far away from villages to avoid detection, considering they are trafficking people where they're working as slaves. But on the other hand, you might want to be close to get like relevant resources that you might want to keep. So we're not sure how to adjudicate this question, but on balance, we want to include it because we think there could be some signal there. And a final thing to say is about other sites. Given that there are like relevant friction costs associated between like setting up the sites and maybe want to move people around between different sites, we think there might be some clustering of the charcoal sites. So this is our initial intuition. And given that information, we want to then go ahead and try extract the relevant features from our data set. So this is what our feature construction pipeline looks like. So first, we look through the data sources. We do some exploratory data analysis and some thinking as well to determine what are the relevant data points which might have signal. The second is the appropriate metric we want to then construct. So for example, we might want to look at what is the shortest distance to a road, how many charcoal sites are within 10 kilometers of an existing charcoal site, what municipality is it in, does that have a difference, and so on. And then finally, we would just gather all of those things together and then construct the actual data and gather it all in GeoPandas, which we then can then feed directly into the model. So I'll talk a little bit more about what we did for each step. So for the data source, we had 3 important data sources. First was SmartLab. So this contains survey data of every municipality in Brazil, and it includes data like the literacy rate, the poverty rate, the number of workers rescued from slave-like conditions, and so on. You can imagine this is straightforwardly a proxy for like how wealthy a municipality is, whether or not that might be important for whether people get trafficked or not. The second is geographic features, which includes the geometries of things like roads, lakes, towns, indigenous lands, deforestation permits, and so on. I think straightforwardly, as I explained earlier, these things all are probably have some signal to determine if there is a true positive charcoal site. And finally, we have map biomass alerts. So this is a data set that is maintained by the Brazilian government using a similar satellite detection process. But what they're looking for is deforestation areas, that is, like trees being cut down, and they can pick that up with satellites. And they update this data set every 2 weeks. So for constructing our metrics, this just requires a little bit of thinking. So on one hand, we think it makes sense to ask like how many charcoal sites might be within 10 kilometers of a charcoal site. So this is like our density metric. Similarly, it might also make sense to ask how many lakes are within 10 kilometers of a charcoal site, or water masses, or how close it is the shortest distance to it, because you might think that if we're very, very close to a lake, that might be not ideal because the soil type is wrong, or there's too much vegetation, or the tree type is wrong, and so on. And if it's particularly dense, then you might think like, oh, well, it might be like a marsh or a bog or something like this, which all has a bearing on whether or not you might want to set up a charcoal site. Cool. So with all this said, what did we come up with? So here's the distance to nearest water mass for true positives. in general, I think the data aligns with what our expectations, and the water mass variable is proxying for other features. So notice that at the 0, there is nothing because you would be surprised to find a charcoal site on water. And at the very furthest, like it's probably not going to be too far away from a water source, given that water sources are generally like land is a bit more flat and it's a bit easier to grow trees and so on and set up your charcoal production sites. You're not driving up mountains to transport your charcoal. So how does this compare with the false positives as well? So you can see here there's like reasonable signal between like a large amount of false positives occur within like quite a small distance from a water mass. So we think between here there is some signal for the model to pick up on and discern between the true positives and false positives. So these were some initial promising results. So what we did is went ahead and constructed every feature that we thought would be relevant and proximate to determining whether or not a site exists. So in total, our full feature construction looks like this. We have 14 distance variables, so shortest straight line distance to features. We have 3 density variables, so that is the feature count within a 10-kilometer radius. We have 12 land cover categories. So what this means is that what type of land is it? Is it a forest? Is it a savanna? Is it a lake? And so on. And then we have 9 survey variables from the Smart Lab data on poverty, the literacy rate, number of rescue workers, and so on. So Kyler will talk now about how we trained the machine learning model.
Right. So everything that we've done up to this point is basically to train this machine learning model. But before we can actually train it, there are a couple important considerations, such as grouping and stratification. And then within the training the machine learning model, there's like different model architectures. And then afterwards, it's all about getting the best performance and then analyzing our results. So first, there are important things to consider whenever handling the training and testing splits of our data. The first is grouping. So as Leon mentioned, in our data set, there are charcoal sites that have been photographed repeatedly over several months through like time series data. And so an important consideration is grouping all of these locations into like one sort of parcel within train test splits, because you don't want leakage of data between like train and test. If we didn't do that, then it would drastically overperform the model. We would drastically be overestimating our model's performance because obviously the model could just memorize where the charcoal sites were. Another important consideration is stratification. We don't want, so obviously we have like an imbalanced data set because most things are not charcoal sites. So it's important that we ensure that every single like split in the training data and testing data has approximately balanced labels. We don't, and that basically ensures consistent results across multiple runs and consistency in our evaluation. And then finally, just for the way we split the data, we had a 1/6 holdout set, the remaining 5/6 broken into 5-fold cross-validation. Within model architectures, we tried a couple different models. The state-of-the-art for these sorts of tabular tasks are mostly like gradient boosting trees and random forest. We also tried some transformer-based models that were very new, like one called tabular PFN. It did not work that well. So, I mean, obviously model architecture is kind of just trial and error. And in the end, we went with a gradient boosting classifier. So after we trained the model, obviously it's important to sort of just squeeze out the best possible performance. So we conducted like hyperparameter tuning, which is just making sure like the individual parameters in the model are the best possible for the task. As you can see, we have some like sorts of test runs here that shows that we're getting a good number of trees in order to ensure good, like maxing out the model's performance, as well as here we can see like the min sample split, which is just a hyperparameter in the model that tries to prevent overfitting. So after all that, we basically have, this was our performance from the model. Precision is basically out of your predictions, how many of them were correct. Recall is sort of like out of reality, how much of the truths did you capture, and then F1 score is sort of a holistic measure of both of these scores. These scores obviously are not the sorts of scores you would see, like winning a Kaggle competition, but I think considering we're in a very different environment, we're building all of this data from the ground up. This project is completely being trained from, like, starting from zero knowledge. And so obviously there's still a lot of improvements to be made, but I think this is really promising to show that we can augment the post-processing of the first stage of the model in order to really make sure that like the real humans, the Brazilian authorities, are not wasting their time looking at like a picture of a boat in the ocean that's been mistaken for like a charcoal site. So within that, we also analyzed how our model was making these predictions. And so this graph here in the gray is essentially the predicted probability of a charcoal site. And this shows that our model is making good distinction. Basically, it would be bad if it was just like a hump in the middle and it was just kind of like arbitrarily putting a line down for where it thought what was or wasn't a charcoal site. But as we can see, there's very strong distinction between what the model thinks is and isn't a charcoal site. Up there, you can see the predicted probabilities by ground truth. So for the negatives, it is predicting pretty much all of them as like 0 probability, which is very good. And then as you can see in the positives by ground truth, there is like the big spike for the true positive charcoal sites. There are, as you can see, a little bit of a spike there at 0. So it's making some mistakes in terms of false positives. After that, after we've trained the model, we also want to analyze feature importance because that may be able to inform us in the like the real world scale of the problem. And so these are 2 different measures of feature importance. This one in the blue is the built-in feature importance from gradient boosting. As we can see, some of the most important metrics were like model score, which is the predicted probability from the original, the first stage of the model. You can imagine that's important because no other features really capture the information from the image itself. Other important things were like distance to nearest water mass, and things like deforestation permits, distance to densely infrastructured areas, and deforestation alerts. Another method that we used, TreeShap, captures a pretty similar results in terms of what features were important. And so that is pretty cool to know going forward and informing future development of the model. Finally, I'd like to talk a little bit about cluster analysis. So like people in the human trafficking data lab and their collab from their past task force deployments in Brazil, there was sort of a heuristic that like, maybe as Leon mentioned earlier, there was some sort of like clustering in charcoal sites. So we definitely wanted to look into that. So our first approach to clustering was geospatial clustering, which is basically only looking at its place in physical space. As you can see here, there appear to be like some clusters out of the 103 distinct locations for charcoal sites. We could cluster like 86 of them. And then a lot of them you can see fell into these pretty big clusters. This could be useful in the future for like just important places to monitor and high risk, because while we are in machine learning in physical space, this is still the same physical space. We're in the state of Maranhão where real things are. And so this is could be pretty important to informing future analysis. We also attempted to cluster by full features. So instead of just like its location, we're talking about all the previous metrics that we used. It didn't really produce anything meaningful, but I think it was worth a good try to see if anything interesting popped up. So I guess finally, in conclusion, there's a lot of future work to be done here. This isn't like a model that's never going to be put into deployment because it literally already is in deployment. like one example of ways we could improve for the future is getting feedback from fieldwork. In this month of August, so like right now, the Brazilian Federal Labor Prosecution Office is deploying a huge wave of task forces out into the field. And this is all informed by the model, not our model, because I'm assuming these operations were planned before we even got here. But this will give us a lot of really important feedback and hopefully rescue a lot of people. A couple other ideas that we had was, since we saw that the first model score was so important in feature importance, we thought maybe we could embed more information from the original image, such as using some sort of like vector embeddings or feature identification that could pick out like kilns or barracks or things like that, as well as improved time series modeling. In the sort of the same vein as clustering, we could try to create a feature that is like how many charcoal sites were in the past. So even though we have charcoal site density currently, just sort of increasing that amount of time series modeling, as well as looking at like when the deforestation was occurring. So there's a lot of room for improvement, and we are very optimistic that this can make a big impact in increasing the efficiency and impact that the task forces can have. So finally, for acknowledgements, we of course have to thank Ben. He was just such a great mentor for us, and we learned so much from him. Thank you to Dr. Mahmedjan. It was great to work with him. Just every week, it was great working with him. Of course, thank you to Kim and Jonas and everyone in the Human Trafficking Data Lab. They really filled in for Ben, and those are no small shoes to fill for whenever Ben was on paternity leave. And then, of course, thank you to everyone here at Shalon, Dr. Naras, for making this program possible. I think I can say on behalf of all of us that we learned a lot this summer, and it was just a really great experience. So thank you.
Are there any questions from the room or from Zoom? If you're on Zoom, you can put a question in the chat, or you can just unmute yourself and jump in as well.
Less of a question. Sorry.
Okay, no, go ahead.
This is Mahmedjan. I just less of a question. Just want to say how thankful we are. Let me see. I'll come off of. Just want to say how thankful we are, like the work building up the pipelines that you folks did, and setting up the test train splits and that kind of stuff. All those investigations, you moved us ahead by several months, much faster than we could have done by ourselves. So I just want to say thank you.
Thank you.
John.
Yeah, so just to echo what Mike said, I think this is really lovely stuff. You should be very proud of it. One of the things I like about it, but maybe this hasn't been investigated much, is, you know, in all of these situations where we bring machine learning into existing situations with the idea of relieving people's work, there's always a little bit of a tension between the people who feel that maybe you're trying to replace them and get them out of a job. I think this particular approach, I can see this working very well in a cooperative way with the human, such as you're supplying information to them that they can use, and they can feed back to you what things that you know that would help improve the model. I think that's one of the great features of this. It's very much in the process, not fighting against the process.
Yeah, absolutely. I think this is a task in which there's like good collaboration, and there's just a lot, I think, like yeah, thank you.
Yeah, one thing I might say is that I think like there is clearly we want to prioritize recall here. Like the cost of missing a charcoal site is presumably high if we're not rescuing people. And I think like, you know, to some extent we will still always have to have human labelers, because, you know, we can't just label a charcoal site as true if there's really nothing there and waste the prosecutor's time. So yeah, I think this will always be in tandem working together.
Sorry, I forgot what I was saying, but I think definitely at no point will there ever be like task forces being sent out without human knowledge, right? So I think it's just really important that we can, obviously the Brazilian authorities, they have limited resources, limited time, and it's just really important that we can maximize what they're investigating.
Yeah, exactly. With the scale of the problem, it's really helpful to do anything that you can do to improve their life.
Great job. All right. We will now hear from our second team, the Free to Feed team.
Good morning, everyone. Thank you so much for being here. We are the other DSSG team, and we collaborate with a company called Free to Feed, and this is our final project. Before we begin, we wanted to introduce ourselves. My name is Nesamoney. I am a rising sophomore, and I'm a bioengineering major.
Good morning, everyone. My name is Amira. I'm also a rising sophomore, and I'm a computer science major. We would also like to introduce our mentors who helped us throughout this journey. We introduced Michael, who was our technical mentor, as well as Dr. Trill, who's joining us on Zoom, who was our faculty mentor from Free to Feed.
So before we jump into our technical process for the summer, we wanted to provide some key background information on our social issue. So to give a brief overview, food allergies are a growing public safety and public health concern that affect almost 8% of children in the US. So that's roughly 1 in 13 children, or 2 students for every classroom. Now, according to the CDC, the prevalence of food allergies in the US has increased by 50% since the 1990s and is now affecting nearly 32 million Americans. And a fundamental issue that informed our research and the mission of Free to Feed is this gap that exists between the number of parentally reported food allergies and actual documented diagnoses. A study conducted in 2016 found that 7.6% of food allergy cases are professionally diagnosed. However, more than 11% of parents believe that their children have and struggle with allergies, regardless of their ability to receive and access care. And so this gap that exists and sort of perpetuates the domain of food allergies leads to several problems. Ongoing food reactivity problems can then develop into life-threatening conditions and even chronic conditions. In addition, current medical providers often fail to offer adequate care and approach plans for their families. In addition, the continuous requirement of medical visits puts a significant financial strain on families. So the aim of our work is to use survey questions and sort of survey respondent data that ask specifically families about foods consumed by children and parents, and to understand the scope of symptoms, the severity of symptoms, and to put food reactivity into a social context.
So to address the issues that Sean mentioned, our project is divided into 3 main aims. Our aim 1 is understanding the initial presentation and progression of reactivity in children. So we're looking at information provided by the parents about how the symptoms occurred, what was the first reaction, to better understand what are the initial presentation and generally seen patterns. Our second aim is more related to the dietary modifications the parents make towards their diets or the diets of their food reactive children. Those are mainly either reintroduction diets to directed through children or elimination diets that lactating parents follow. And we think that analyzing these questions can also help us understand the general patterns that parents follow and addressing their food activity in their children. And lastly, to put the issue in the social context, we explored the information parents provide about different health disparities and expenses-related issues that they face on their journey tackling food reactivity. And we hope to put this information into social context to better understand the struggles that these families face and draw attention to these issues.
So the data that we used this summer was collected through a survey that was disseminated by the Free to Feed team. And the data was primarily parentally reported food reactivity case data. In total, 558 surveys were filled out, and this corresponds to 558 individual children. However, there are some cases where one parent is filling out the survey for multiple of the same children, for multiple of their different children. There was a combination of free response textual data and multiple choice questions. And in total, 172 variables were collected. And so on the screen now, you can see two examples of types of questions that were asked in the survey. On the left side is one of the typical free response questions, and on the right is a multiple choice question. And so sort of to conclude our overview of this topic, we wanted to provide information about the ethnic demographics of our sample pool. As you can see in this figure, a vast majority of survey respondents identify as white or European American. And we thought that this information was pretty essential, especially when starting discussions about how this project fits into a social context and who are some of the most vulnerable populations to the issue.
So once we started analyzing our data, we came across this realization that the data in the way it was provided to us was not ready or was not convenient for analysis. And the reason for that is, as Sean mentioned earlier, a lot of our data contained were free text responses towards the different questions in the survey. So while, as you see on the screen, another example of a question in the survey, and while the respondents were provided a certain pattern to follow in their responses, obviously they're humans and they make mistakes, they make spelling mistakes, different capitalizations, and a lot of parents didn't even follow this pattern. So that's when we realized that we would either need to manually go through our data and extract the information that we needed. But however, since we had more than 20 text response columns and we needed a lot of them to make the analysis that we wanted to make, we wanted to look for other potential ways to automate the process. And the solution that we came up with was utilizing large language models. Specifically for our project, we used OpenAI GPT-4o model in order to extract the specific data that we want from the text responses, to generalize it. And Sean is going to talk more about specifically how we did that, but generally, while we could not like 100% say that the model didn't make any mistakes, it was still a lot more time. It was a lot less time consuming to go through the model's results and clean the mistakes made instead of cleaning the whole entire column.
So to show how we were able to utilize the API to transform our sort of noisy, cluttered data into a clean format, we generated this visualization. And so we'll start on the left side. In the red box shows how the data was presented to us. And right below it, you can see actually a little snippet of what a parent reported, saying that dairy was removed at 4 weeks and soy at 3 months, and then remained dairy and soy free for a whole breastfeeding journey. And so as you can see, there are a myriad of ways to communicate that you were eliminating a certain food out of your diet. You could say it was removed, you could say you went this food free. And so it was our job to engineer prompts very carefully and thoughtfully in order to tell the API exactly which information we wanted extracted and how we wanted it presented back to us. And so as you can see, that hollow arrow at the bottom shows a prompt that we would tell the OpenAI LLM to output the information as follows, putting the food trigger followed by how long a food was eliminated for and how long it took before the child experienced an alleviation of symptoms. And so in this middle column highlights which features we wanted extracted. So what foods were eliminated, how long, and how long before alleviated. And then on the rightmost side, this is what sort of GPT-4o produces for us, is an array of information followed, an array of information, and each entry is exactly how we asked them to present the information to us. However, a long array of strings is hardly usable when it comes to sort of the analysis we're trying to do. So then we follow that by just iterating through the array and populating a data frame. And we used regular expression to look for specific patterns just to make that process a little bit easier.
This is another example of the column that we cleaned which should answer the question, what is or was the child reactive to? And parents were asked to fill out 4 data information in this column, such as triggers, IG, category, age of first reaction, and symptoms. And as we can see, it's very noisy on the left. And after putting this column into through LLM, and after the model adapting the information with specific format that we asked it output it with, for example, we could ask the model to use dashes as delimiters. We used the standardized responses that GPT-4o gave us, and we can then split the data like this, and it's much more easy to analyze it, and it's very standardized. So now going to our first aim, which is understanding the initial presentation of food allergies by looking at symptoms and triggers. After cleaning our data, we were first looking to look at what are the most common symptoms that children in our data experience. And here you can see this bar chart, and the most common symptoms were eczema, lupus, vomiting, diarrhea, reflux, and discomfort and hives. And this just shows us that these are very serious symptoms, and children in our data experience it from very early ages, just highlighting how the struggles that families and children face. Next, we wanted to look at the triggers that cause these symptoms, and on this plot, you can see the top 10 triggers being peanut, wheat, oats, dairy, peanuts, rice, vegetables, eggs, corn, and soy. And we also mapped them to sensitivity levels that the parents were asked to report. High being that they cannot interact with the tumor at all, medium being they can interact with cooked versions, low being they can interact with small amounts, and etc. As we can see, for all common triggers, majority of the parents reported their children to either be high or have medium sensitivity to the trigger, with peanuts having the highest sensitivity levels and soy being the most moderate. And this just once again highlights that the children have very high reactivity levels at early ages, and it's an issue that's very hard to maintain.
So our second aim addresses dietary modifications and treatments that parents may be trying out during the study. And so the first the first dietary modification we looked at was elimination diets. And elimination diets are a diagnostic approach that a lot of individuals use through a series of trial and error of excluding different food items from their diet to pinpoint which trigger exactly is sort of causing the most amount of symptoms. And so this chart shows how long elimination diets lasted for across all the individuals in our data set that indicated that they tried out this sort of dieting approach. And so as you can see, the most common lengths of diets lie on the 2 extremes in our data set, with the most amount lasting over 20 weeks and the second most lasting within a week. And we think it was really important to acknowledge how the question was phrased in the survey, that we were asking parents how long it took before they reached the perfect combination of foods to reduce the symptoms the most. And so as such, this makes sense that most of the diets lasted over 20 weeks. just finding the perfect combination of foods is going to require a lot of sort of reiterations of trial and error.
So another dieting modification parents made was related to the children themselves. So these are reintroduction diets, which means that once the trigger is identified as a known trigger to cause reactivity, the parents later on in their child's life try to reintroduce it and see if symptoms change. And one question our data set asked for success cases or failure cases in all the introduction attempts that the parents made. And here on this plot, you can see the success rates for all for top 10 most reintroduced triggers, with highest success rates being for tree nuts and peanuts, around 80%, and lowest being for dairy, oats, and avocado, below 45%. We found it interesting that dairy, being the most common food trigger, has one of the lowest success rates. This is also given that some parents try to reintroduce the same trigger multiple times throughout their child's lifespan. And this just, once again indicates the complexity of the reactivity journey.
So our third and final aim asks about some of the social implications of food reactivity. And for one of our first forms of analysis, we looked at how families of the data set experience different health-related disparities. And so the questions that informed this analysis came from a collection of yes or no questions asking parents to indicate whether they have experienced a specific disparity that was presented to them. And so this plot sort of just summarizes what are the most commonly experienced social determinants while sort of combating their child's healthcare journey. And as you can see, the majority of parents, exceeding 80% of the survey respondents, experienced increased anxiety, stress, or trauma. And this finding wasn't super shocking to us, given that sort of battling severe food allergies for an infant child is a very sort of stress-inducing experience. However, one question that was informed by this finding was what is the source of this anxiety, stress, and trauma? Is it primarily caused due to the severity of symptoms? Is it caused due to other social determinants? Is it caused to the financial strain that it puts on families? And so in a few slides, you'll see another sort of form of analysis that we conducted to understand where does most of the family's stress and anxiety and trauma come from. The second variable we looked at was seeing how did food reactivity affect families financially. And similar to the health-related disparities, these findings came from data that asked families just to indicate yes or no if they experienced increases in spending for different items related to their food reactivity journey. And as you can see, a vast majority of our respondents indicated increased spending in things like specialty foods and formula, specialty provider visits, primary provider visits, and other medications. And similar to the health disparities finding, these weren't in any way very shocking to us, but rather served as a testament to how personal food reactivity is, especially for children, and requires sort of extensive clinical visits, requires healthcare professionals that truly understand your family situation and your child's healthcare needs. And so, as I mentioned 2 slides before, we finally, both of these findings informed us to look at how our health-related disparities correlated to increased expenses that these families may be experiencing. And so we first generated this correlation matrix and visualized it in a heat map. And there were a few correlation coefficients that we wanted to draw your attention to, as we found them pretty interesting. The first of which was seeing somewhat of a correlation between a caregiver having to leave their job. And so that is a health-related disparity that was faced by this family. And as a result, they experienced loss in wages. So this relationship made sense. And I think relative to some of the other values that we got from this matrix, this one stood out as one of the most sort of positive leading. Our second value was a correlation between families having a difficult time obtaining childcare and an increase in sort of childcare related spendings. And again, this relationship made sense. And finally, families who had a difficult time with or had increased health insurance related spendings found themselves sort of slipping into states of medical debt. And so all three of these values just seem most salient in the matrix, just based on how robust their number was. And when we took a closer look, their relationship was sound.
So last variable that we looked at tried to see if it somehow affects families' expenses was the number of food triggers that a child has. So we grouped the children in our data set by the number of food triggers that their parents reported for them, and we plotted this to see within each group how many said yes to a certain health expense question. And we can see a very clear upwards trend with the more food triggers a child has, the more likely their families to experience food reactivity related expenses. And we can see it for almost all categories. It was also, I think, important to note that the data set was quite evenly distributed in terms of the number of triggers. So we had around 100 respondents in each category. So this is a very interesting graphic that we found. And also, it was not a surprising information because it is expected that the more your child has different triggers, the harder it is to then cover all the different expenses for that. So after we did the analysis, or generally throughout doing the analysis for these 8 weeks, we realized, and after also understanding how much time we spent creating the data, figuring out the best ways to do so, we realized that our data set is strongly limited by its structure and the way the data was collected from the respondents. And given the fact that Free2Feed is an existing company and is going to continue its research in the future, we wanted to explore different ways we could enhance this research process for the future work, and generally just we're thinking about the ways that this data collection and data cleaning process could become more convenient for the data science researchers. And one of this approaches that we came up with was redesigning the survey. So as we showed you earlier, the different questions in our survey and the way the struggles that we faced while trying to extract data from that, we thought that one of the most direct ways to address this challenge that we faced was just getting away from the extensive pretext response data and having more standardized, streamlined questions. And our solution was integrating Qualtrics. So the survey initially was conducted on a different platform called 123 Builder, and it was a one-page survey. And instead, we decided to use Qualtrics, which is a popular platform for survey development. It has different functions such as survey flow, generally has more diverse types of questions, and etc. So there were many different ways we thought the survey could have been enhanced, but maybe to point out a few for you was that the before survey did not have a survey flow, and this was mainly an issue because some families that had more than one food reactive child had to fill out the same questions several times. So they were asked to fill out the same form for each of their child. However, some of the questions within the form were family related and not child related, such as health expense questions. And this was actually an issue because when trying to analyze health expenses, we realized that the same family reported different information just because it's hard to keep track of all the data that you inputted before. And to address this question, we created survey flow in our Qualtrics survey. So the way the survey currently works, the survey that we redesigned works is it first asks for your general family information like email address, last name, and then it takes and then it asks you how many reactive children do you have, and based on your response, it takes you into this loop where you answer the same questions for child-specific questions for each of the reactive children. And once you're done answering child-specific questions, it merges you back into the main branch and asks you for family-specific questions. And this way, one parent has to fill out the form only once. and there's going to be less discrepancy in the data, etc. So just to show you how, like an example of standardization of the survey, I wanted to show you the before and after versions. So on the left, you see we decided to go with the example of the question, what is the child reactive to? And on the left, well, the parent had to manually input all the data. There was a chance of making mistakes. On the right in Qualtrics, parents just select from the standardized food triggers, and then they're taken to a new page where the data that they inputted from the previous page is carried forward, and they only have to fill out information for the food triggers that they selected. Everything is standardized, the age is standardized. There's very little typing that they have to do. And same for the symptoms, they just select from the predefined list for them. We also got the lists of triggers and symptoms from pre-defeat. And yes, currently the survey is almost finished. We're just polishing some questions and discussing that with pre-defeat, and we plan to submit this to them as a proposal for their future research. I thought that this was an interesting finding. We didn't expect to tackle this area of survey engineering over the summer, but it was very interesting to do so.
So to conclude our presentation, we wanted to share some of the takeaways we had from the past 8 weeks, some of them which are specific to the content of our project, and some of them which just relate to research as a whole. So first and foremost, we have just come to realize through this project that food allergies are a significantly impactful aspect of the lives of children and families who struggle with them, and that they can start as early as infancy. I think before this project, my sort of preconceived notion of food allergies was that it's something that young toddlers maybe deal with, and completely sort of failed to understand that this is an issue that parents have to struggle with immediately after birth. Secondly, food reactivity can vary in severity between individuals, and so this just goes to show how important personalization is when either crafting healthcare plans or sort of strategies for families to employ in their own households. Third, like all health-related social issues, food reactivity must also be examined holistically in order to understand the true extent to which it impairs individuals. So this means understanding not only how symptoms are manifesting, but also what social determinants might be in the way of a parent being unable to access care, or being unable to provide for the proper medication that their children might need. Fourth was something that was just discussed, was the importance of survey design, especially in observational data. Not only does your data become more robust when your survey is as efficient as possible, because it ensures that respondents are as engaged as possible when they are filling it out, and you get the most of from very little sort of work on the part of the respondent. But also it just helps sort of data scientists on the back end of things to sort of play with the data and use it to its full potential. And on a similar line, this project really sort of showed us the power of a data set, especially a small data set. We worked with only about 558 respondents worth of data. However, we were able to extrapolate a lot of information from it and take away a lot of important sort of conclusions from this project. So it sort of goes to show for future projects down the line that you can sort of discover a lot from a data set, no matter how large it is. And so we just like to thank you for listening, ask if anyone has any questions, and also give a special thank you to Michael and Dr. Trill, who's on Zoom, Naris, and Shalon, and the Free to Feed team for all of their support in the past few weeks. Thank you.
Any questions, comments?
I know this isn't super related to your project, but do you have any thoughts on like that first figure you brought up, where like allergies went up by 50% since then?
Oh, yeah, so in literature review, like in literature, it says that it's mostly, like part of it is that like there's more research and people are like know better how to diagnose food allergies. And on the other hand, people nowadays are more likely to like suspect the food allergy. So like beforehand, they would just think it's something that everyone lives through. Now they're more likely to just go and like explore what their child is going through. So like the rise in awareness and like research.
Any other questions on Zoom? Oh, there's a hand up somewhere.
Yeah, hi there. This is Libby. Thanks for your great presentation and sharing some of your findings. They're quite interesting to see. Some questions were, you were mentioning like one of the big takeaways was the importance of survey design. So I'm kind of curious about what are your thoughts after this process in terms of between allowing like more expressive responses, such as through the free form responses that you initially like looked at and that you were able to kind of parse using the GPT architectures versus the more constrained structured responses, such as through the survey that you kind of ended up with. And what are some things that, what are some aspects of the responses that you may be trading off by going, like that you can't do now through the survey?
Yeah, I think this is a great question. And I think something we definitely grappled with was, especially for health-related data, it's really important to sort of get the whole picture from sort of your patients. But I think it also really depends on what you see as the purpose of the data set. I think, for example, we were in a meeting this past summer and we were sort of questioning whether we could look into if, I think Amira mentioned like reintroductions and then also if there's a difference in like reintroduction that the parent is reintroducing it and they're sort of breastfeeding their child versus you're reintroducing like solid food to the child directly. And so for like a case like this, I think detail is really important, especially with having the respondent specify whether it was reintroduced through breastfeeding or through just solid food. However, I think we also recognize that there are ways to sort of make the response process just more efficient for individuals. So like rather than having them explain the whole process of how did reintroduction happen, rather just specify the food that was reintroduced and the method that it was reintroduced by. And also, I think when we're looking at like a population or like a sample pool, we're also just looking for trends on sort of more initial and surface level glance. And then I think seeing if that's a pattern that stands out, I think detail can also come in on sort of patient healthcare provider side of things. So I feel like, and Amira, if you have any thoughts as well, but I think when it comes to the application of data science for this purpose, it was really prioritized to see what is sort of what patterns are appearing most.
I agree with Sean. I also think that it's important to acknowledge like the size of our data set and given that in the pretext responses, yes, while parents gave some very thorough responses, they were giving details on different things. So like 10 people can give more details about like what type of dairy their child consumed. The 10 other people are going to tell more about the timeline. And it's just, it was like, because our project was mostly looking at like the bigger picture and trying to aggregate the data. That was the priority. We thought that like losing that information was a bit less like important than trying to standardize what we call the main points. However, yes, we do think that maybe I think that's just like a different type of research. And it's more like a case study research where you can get the most of the details that each parents provide. So yes, we have to. It's a great question. We do consider that.
Great, thank you. Yeah, I think there's always this tension between how you take in the data and how you process it, and it's I think it was very informative to hear you guys share that experience of going through an iteration of that. Thank you.
Thank you, everyone. Great job.
But I just want to thank everybody who made the DSSG 2024 happen. In particular, I want to first thank the PIs, Dr. Tilkat Paulin, and my bio team for having the project in the first place. But of course, the biggest thanks to the students who actually did the work. But their work would not have been done without the amazing mentors they had, Michael, Shilan, Annie, who's online, I guess, and then Ben also who's online, and also the associated team. So thanks, and I hope you had a great time. We did certainly have a great time hearing you all progress through the 8 weeks and ending up with this final presentation. So once more.
Comment, John Chambers. I think all of you will find that the lessons you've learned here are really key to data-intensive science. Things like both the teams found that interacting with the people who are producing the data and giving them advice on how more could be learned from the data if they made some changes. These are things that are absolutely crucial to this whole area. I think we've had a great experience.
All right, let's get some donuts.
All right, that concludes, I guess.